Happy Friday and welcome to OSI's webinar. Thank you so much again for joining our webinar, and thank you for showing the patience and rejoining the webinar since we had technical issues yesterday. I am Shivani Vyas. I am a petroleum engineer and I'm a technical services engineer with Odessa Separator. Been with the company for about 3 years now, and today with us we also have Donovan.
Hey guys, thank you for joining our webinar. Happy to see some of y'all here. This time we'll try and get through without any technical difficulties. I'm also a technical services engineer, and I've been with the company for about a year now.
Yeah, and hopefully all of you guys are safe and sound, and hope all of your family members are also safe and sound in this unprecedented time. And we definitely want to be in touch with you guys, and just want to discuss. I think this is a good time to just sit back and analyze some of the things. And we thought common failures in the Permian Basin would be a great topic to go ahead and analyze, just because we've all experienced it. And not only because of that, but it's also given us the knowledge to go ahead and analyze the failure, but also have the ability to go ahead and improve on it. And we've definitely improved on some of the things that we've not seen earlier in the basin. And that's exactly what we're going to go around, is see what are the recent failures and how have we overcome these failures. So why are we talking Permian Basin? Is yes, we are on this basin, but also because this is the world's finest deposits of oil and gas. And as we know, it's made up of 3 basins. It's Delaware Basin, Midland Basin, and Central Basin. And as we can see, Delaware Basin is much deeper than the other 2 basins, which means that it has more capability for drilling more wells and having more production versus the other 2 basins. Also, another thing to note here is the deposits of shale around the basin. All the gray areas that you all see around the basin is the shale deposit, which means that we've become capable of drilling through the tight formation. And that's what created shale revolution, and Permian Basin is a big part of it. So whenever this happened, the shale revolution, what happened is the U.S.'s production picked high up. That's exactly what we can see here, is in 2000s, the production started picking up, and Permian Basin was a big contributor of it. And in about, we can see before that, for about a decade, the production was steady, and Permian Basin contributed about 22%. And whenever this revolution started happening, we started producing so much that in the past couple years, let's say in 2018, we surpassed the number 1 and number 2 producing countries, that is Russia and Saudi, and became number 1 in the US on the strength of Permian Basin. And we can see on the numbers of oil production too. In 2012, we were producing about 1 million barrels of oil per day, which we increased to 4.1 million barrels of oil per day, which means Permian Basin contributes 40% of US's oil production. And so with the increasing technologies and with the increasing activities, what we've also seen is some of the things that we did not face before. Like, let's say the lateral in 2015 was 5,000 foot lateral average, which in 2018 increased to 8,000 foot lateral. So which means that the sand production has also increased, not only the formation sand that we're having, but also the frac sand. The amount of frac sand that we are having per foot lateral has increased so much that we are going to have some sand problems. On top of it, we do know that the horizontal wells, the lateral, has a tendency to have that slug formation come in and have sudden sand production come in onto the production of the well. So one of the things that we've recently seen is this. What happens is we have cut desander. Now, the desander, how does it work? Is we're going to have the outer body and the inner body, which makes the sleeve of the desander. And then we have a helix, which creates the centrifugal force, the main part of the descender that goes ahead and creates the centrifugal force right here to separate that fine particles and dump it into the tailpipe, and your cleaner fluid goes back up into the tailpipe, or sorry, back up into your pump production. So whenever we have so much production that the velocity of the fluid is so high and it creates so much radial force that wherever there is not a double sleeve and a weak portion gets affected. In this case is here, the thread, which is the weakest portion. And so one of the cases that we did analyze is we can see that we did cut the descender in two parts. And what we observed was internally, there was a lot of erosion and corrosion. So we can see the effect right here. And it is right below, few inches below this vortex. So what we're seeing is wherever we have that radial force right here generated so much that that part gets affected, and it then gets transported to the weakest portion of that descender. So before we do that, let's go ahead and see how does the actual descender work. And that's what we've done a test on our lab itself. And we can see right here. So this is where we're dumping different kind particle, sand particle inside. And we can see how inside right here is your helix. And now you're generating that centrifugal force. And we can see all the sand particle is gathering right here. And so let's say if that fluid velocity is so high that it's creating that turbulence that it cannot handle, the weakest part will get damaged. So similarly, that's what we found in one of the wells, and I believe this is the Martin County, where this well was producing about 3,000 barrels of fluid per day, and a descender was sized to handle. The first life of the well was going to start at 3,000 and was going to decline at 800 barrels per day. And we were using a cup packer, so we can see right below the ESP, we have the outlet section, the cup packer, the isolator, we have the inlet, and then the descender itself. And we have the 2-foot descender right here. So now this well had an unexpected frac hit, which the producer was not expecting. And obviously we were not aware since the producer was not expecting either. So what happened is just in a few hours, this well started producing about 6,000 barrels of fluid per day. Now, the descender did its job, but whenever this was double than what it was designed for, it got destroyed. And we can see right here is what we found out was exactly the same thing. Your threads are going to get destroyed because that's the weakest part. And then your internal erosion that happened in this one. And we can see what we talked about before was the radial force. That had the highest effect internally in the vortex. And we can see right before that, it did run for 154 days. But since it had the frac hit and it doubled its production for a few hours, it went ahead and did destroy. So whenever our R&D team right here, what we call the moonshine team, did go ahead and analyze is this is what we found. That, okay, radial force does have a great effect on it. And what are the things that we can go ahead and do to improve and optimize just in case that we are going to face problems like this? And so what we did was let's go ahead and understand the radial force now that we have. How about we go ahead and increase the length? That way we can control the radial force and the velocity, even in case that it goes high up, way more than we've designed and expected it. And let's go ahead and see that. So we did go ahead and increase the length from 2 foot to 6 foot, and then the same design that's been working for 224 days and still working, no problems on it. Also, another thing that we came up was if we have high resistance material, which was not in this well, we used the same material. But what we can see is we can go ahead and use that as well and have it double walled. That way it can go ahead and control that centrifugal force and the radial forces on it.
So one of the other big issues that we can see when maybe you have a little bit more sand production than you expect in the beginning, or you're a desander, or you get hit with a frac hit or something like that, is some plugged intakes. And you can see that on your ESPs and your rod pumps. So you can see your plugged intakes due to sand on the sanding valves, and that just starts to create erosion and then secondary failures. And then on your ESPs, you can see a lot more sand get into your pump stages and then start eroding those impellers and creating more failures. And another way we can see plugged intakes will be the creation of scale, as you can see on the ESP to the left. But we will get into the chemical side of that later. Shivani will go over that. What I want to go over right now is when you get hit with the frac, your neighboring well. In the bottom right, you can see that this is a mud joint and it's been filled to the brim. So what can you do at that point if you have your intake plugged or you have a dip tube and your mud joints fill up way faster, maybe in a couple of weeks or a couple of months when you design for it to last longer? This is where we can start to see a new design of the bypass valve. And the bypass valve is an optimized solution that Odessa Separators came up with. And as you can see in the bottom left, the helix is the sand is filled up all the mud joints, or this is a slotted intake and the sand has plugged the intake. What the bypass valve can do for you is it's originally closed in the beginning and is actuated by pressure. So once the intake is closed or the dip tube has been clogged from too much sand from the bottom, the fluid level will start to rise and it'll start to push against that spring where right here, the green section is a spring, and it'll start to be pushed, and that'll be an instantaneous thing. So on your ESP, you'll be able to see the pump intake pressure jump for a split second. So you'll know that it's open, and then it'll be able to, start to open and close a little bit as maybe some of the sand starts to fall off the intake. Or you also have the opportunity to back flush. If you know that's open, you'll have the opportunity to back flush and hopefully clean out some of the sand in the intake. Or if you kind of just want to pull so you don't burn out the motor, because at that point, your ESP, you're going to be pumping dry. You're not going to be pulling in any oil. So that'll overheat your motor, and that can really ruin the ESP and just create a lot more problems that you could solve in the beginning. And the bypass valve is also compatible with any intake that you have. So downhole, rod pump, or your ESP, if you're using just a slotted sub, perf sub, or anything like that, if you have a screen, a desander, any of those intakes, this can go above any of those intakes, any of those separation tools to help give that extra life and basically be an insurance tool to make sure you're not ruining your pumps in the beginning and to make sure you can keep pumping fluid. One of the other big failures we like to see and we don't like to see in our ESPs is free gas. And what can free gas do? That can start to create gas locking in your impellers. So you're going to start pumping dry. It's going to really lower your drawdown. It's going to overheat your motor, and that can lead to a failure. But I'm not going to touch too much on this because we have a different webinar that my colleagues Carlos Portilla and Neil Johnson went over. They had a whole webinar on how to effectively separate gas in the ESP. I just kind of wanted to touch on this because this is a common failure that you will see in ESPs, especially when you start getting to the end of the life and you start producing more gas when your fluid production starts to decrease. And I just wanted to keep that in the back of your mind. But one of the things I am going to go over a little bit more in depth is the effects of free gas in your sucker rod pump. So I'm going to start off with gas interference in the rod pump, because gas interference itself won't really lead to any failures, but it will decrease the efficiency of your rod pump. You'll start to have more gas in your pump, and your pump fillage may decrease a little bit or a lot of it. So that can lead to more gas interference you start to have. You may start to then get gas locked. And when you get gas locked, you're only going to have gas in the barrel, only gas in between both valves, and you're not going to be allowing the valves to open to allow the fluid to flow through the pump. So then at that point, you're going to be pumping dry. You're not going to be able to pump at all. But gas lock in itself, it is bad, but it's not as bad as fluid pound, because gas lock, maybe when the bottom hole pressure starts to increase a little bit, it will naturally start to open those valves. So then we can start getting to fluid pound. And fluid pound is when you're going to start seeing a lot of those secondary failures in the rod pump. When the fluid pound occurs, you can be seeing thousands of pounds hitting that fluid at once to open up that traveling valve. And that can lead to a myriad of failures, such as a tubing failure. When your rod starts to buckle, the rod buckling will come in contact, as you can see here on the left. It will start to come in contact with the tubing, and all that contact with the tubing will start to erode it, and eventually it could start to create a hole in the tubing, or there can also cause some rod failures just from mechanical fatigue from that constant pounding against the fluid. And it can also create mess up the standing valve and traveling valve, start to fatigue those, and then at that point you're going to not be able to pump efficiently or really at all. So this is where we want to put down when you start to see these issues, you really want to put in a gas separator below the pump to make sure you're not going to get that gas lock or that fluid pound. And then when you're separating the gas efficiently, you're really going to start to avoid all those secondary issues that will come from the fluid pound or the gas lock. And you'll start to produce more fluid and produce more efficiently. So this is a case study we did with a packet type separator. If you see the production on the right, they're producing really high gas in the beginning. They're producing close to 400 MCF and only about 500 barrels of fluid per day. And this was at the end of the ESP life. So once they decided they wanted to switch to rod pump, they decided they really needed a gas separator below the pump. So we decided, since this is a really high gas producing well, to go with a packet type separator, because you're going to get more separation at that point, because you have more separation space when you're separating between the casing, the annulus in the casing, and the tubing. So the outlet will be up here, and then this section is where you will start to see that gas separation. It'll be a lot more efficient at gas separating than your typical Mother Hubbards or your modified Mother Hubbards or anything like that. So we decided to go with the packer separator in this well because it had very high gas production. And as you can see afterwards, we pretty much doubled. It had the same gas production, but we were able to double the fluid production. In this case, the reason was because towards the end of that ESP life, the drawdown from the ESP started to be more than what the reservoir was producing. So at that point, it's trying to suck in too much, and it's starting to suck in more gas and fluid. And that was really affecting the efficiency. So even though rod pump has lower capability than the ESP, it more correctly matched the inflow performance of the reservoir and was able to more efficiently fill up their pump than the ESP. So at that point, we were producing 800, even 900 barrels per day in some instances, which is pretty good on the and able to lower the GOR or the GOR very significantly.
All right, so another thing that is pretty common, like we can see here in the pictures, is the constant change in the pH of the water. we all know that whenever we try and solve one problem on your water pH, the other problem arises. And that's why it's so critical to go ahead and analyze the pH every single month. And I'm sure the operator is still a big problem around here. And like here in the pictures, we can see the pitting problems due to corrosion, the scale issues, and now iron sulfide issues, which is pretty big in the Permian Basin, Howard County, Martin County, that it starts with the scale problem initially, and then just with the change in the water, the pHs starts to change into your iron sulfide, which again, as we can see right here, your intake is completely clogged up, and now you are hindering the production on the well. So traditionally in the industry, how we're treating is we're treating from the surface downhole, and it's doing its job. But what we're missing is it's not treating where it needs to be treated, especially whenever we have high fluid levels or we're using a packer, just like on the case study that Donovan said, how are we going to treat something chemically below a packer or with high fluid levels? So what we have done is we want to treat it from bottom to the top, A, because it has to be treated where it needs to be, and B, all the production fluid gets treated before it comes into the intake of the pump. And now we don't have more of the problems that we've seen before. So how do we do this is briefly is we're going to have our solid sticks, either scale, corrosion, THPS for iron sulfide in the form of solid, and just have it below the intake of the pump. That way it disperses just like a tea bag effect. Wherever the fluid comes in contact with that chemical, it leaches out, and then your fluid gets treated chemically and then comes in the intake of the pump. So we're going to go ahead and see some of the case studies of how effective has this been and what was the problem before. Now, this is a case study in Midland Basin where we can see the regulars 5.5 casing, 2.7-inch tubing, and the average production was about 550 barrels of fluid per day. And we can see the oil, gas, and water production, pretty high gas production on this well as well. And the main issue here was severe corrosion and scale deposition, and on scale, mainly iron components. So it's a pretty severe issue of scale and corrosion together. And now this was on gas lift. So what we decided to do is we went ahead and did a treatment on 2 stages. So one was to go ahead and have the treatment just on the tubing itself. So you can go ahead and attach the cam screens on the tubing itself right here that we can see. And then on the second stage, let's say we have decided a runtime for about a few months. And once we have run out of these chemicals, the tubing cam screens, we can go ahead and have the retrievable cam screens. That's why on the initial design, it's really important to go ahead and have this in mind, that if we want to go ahead and have a retrievable cam screen through a slick line, we can have this one get in. And that's why we had 2 tailpipes of 60 foot. So that's exactly what we've done, is we've had a combination of scale and corrosion on the tubing, and then on the retrievable cam screen, here is the 50 foot, 1.25 inch, the same treatment. And also another thing, it's really important to have both the combinations to treat whatever it's formed, and then to treat something that can prevent the formation of the same scale and corrosion. And that's why we see that we have a combination of scale, corrosion, and then acid sulfoctane too. So now this is what we've done, is just how do we go ahead and monitor? Because if we don't monitor on the chemicals, how do we know that we have affected on the chemical as far as corrosion rates go, as far as scale rates go? So this is something that we have the corrosion rates and iron and manganese rates that we can see is initially it started with 1.8 MPY, and throughout a year, it's pretty much gone pretty low to about less than 1 MPY, which is optimal as far as corrosion rates go. And we can see the same in iron and manganese count as well. So iron is a natural component of water. And so that is pretty critical to go ahead and see is how do we manage the iron and manganese concentration, because we do not want too much space in between your iron and manganese, by which I mean that you do not want the iron to go very low and then your manganese to be high up. And now that's going to create problems. So it's really important to go ahead and monitor all of these factors simultaneously. Also, the scale inhibitor. So now the scale inhibitor is all the components, the phosphate components that's been in the water. And that's what we can see is how much is the composition of the scale inhibitor throughout the year. Also, what is the composition of the corrosion inhibitor, which is again your amines. The polytag here is something that tells us that how long is my chemical going to last. So this is one of the questions that is always been asked is, once the chemical is downhole, how do I know that the chemical is still there, right? Which is pretty obvious. So what we do is with X amount of chemical, there's X amount of polymer. So every time there we have the fluid sample, which depends on the operator, is every monthly basis that we do, or every biweekly that we can see here is that's what we've done biweekly, is get the sample and see how much is the chemical still lasting. A, just to check if the chemical is still down there and active, and B, to see what and when is the chemical going to completely go out. That way we can see if we need to go ahead and go out with the retrievable or just the surface. In this case, we have done the retrievable cam screen. Remember the two-stage that we were talking, the tubing, and then with the slick line. Again, the THPS, this is the component for just iron sulfide, and that's what is done in the lab too. That test on how much is the concentration of THPS in the water and how does it react, or how effective has it been doing. Now, this is a case study of ESPs, just to give an idea of what different kind of water per day. Here we're dealing with 6,000 barrels of fluid per day. So we do have to keep in mind that the chemical combination and the length is going to be in accordance with the production, your downhole temperatures and pressures. And so over here, instead of just going with 72 foot of chemical screens, we have 120 foot of chemical screens, because we have so much production, and so are we going to have the longevity of the production, as well as the longevity of the chemicals in the production as well. So let's say this is the design right below the pump, is we have the tubing chem screens, and we can see right here is the dispersion areas, all the screens that we have. So whenever we have the fluid come out of the perforation, go into your pump intake, that's where all the fluid is chemically treated, just what I said, the teabag effect, before it goes into the pump. And also another thing to note here is in between the chemicals or the cam screens is your flow nipple. That way, let's say your joint of chemical right here, the solid joint internally is completely leached out. It goes ahead and transfers, and that's what you're continuously dispersing your chemical. And right here, in between your pump and chemical, is going to be a no-flow nipple, which means that the chemicals cannot directly go into your pump intake. So it has to, your fluid has to be treated before it goes into your intake of the chemical. And so that's why we have the scale and corrosion, just like we had before, is your amines and phosphates to see what is the concentration, the optimal concentration throughout the lifespan of the well since we've had the chemical treatment, as well as the THPS. Has it been effective? Has it been worth the monetary investment that's been done on the chemicals? And just to see if what has been the concentration and the effectiveness after having the chemical screens on it. And that's exactly what I was talking about. Is initially, like we can see here, for a couple months they've had the acid job, where estimate is about $5,000 per acid job. And let's say if we were to run that for a span of a year, we're spending 35,000 versus 120 foot of cam screens is going to be about 15,000, and you're saving that much cost, but you're also running that for a lifespan. Also, I believe here, as far as the information given from the operator, the cap string was plugged. And so the acid treatment was just completely for a few months and completely relying on the downhole chemical treatment. So this is something that's been pretty much optimal, especially the pH and the changes of the pH in the water that we've been seeing recently, just to treat the fluid before it goes in the intake, as well as not plugging the intake.
Thank you, Shivani. So Shivani just went over a couple of case studies with you, gave you some data points on how we can see the efficiency of the chemical downhole and see if it's doing its job and if we're getting the minimum amount or the optimum amount of chemical treatment we should be getting downhole. Here, I'm going to show you some of the chemical treatment efficiency. Give you a visual before and after. See, if you look on the left, you can see they're pulling the ESP, and that thing is just riddled with scale in between the pump and the shroud. See, they continue to pull it out, and it's just everywhere. And this one had 100,000. It had 1,000 barrels of fluid per day, and it only had a run life of 122 days. And the failure was because of the scale that you're seeing. And here on my right, you'll see the installation we had with the same well. So we had about 96 feet of scale inhibitor and chemical treatment in this well. And this one failed after 108 days, but this was due to seal problems, not due to scale problems. And it still maintained its production of around 900 barrels of fluid per day. So I'm gonna push play right here. You can see the difference between an untreated well and a treated well. You see how clean this ESP is compared to the first time it was pulled. See virtually no scale falling off. Here's some other ESP case studies. This is just done to show the operator and how we design with our wells. So the operator really gives us an idea of how long they're expecting our chemical treatment to last, because we can design for that. So we're going for about a year in all of these wells, 365 days. And with this, we can really design for different lengths. So depending on the production, we're going to go maybe 72, 96, 120 feet to get that longevity that the operator is expecting. And they may only be expecting a year due to maybe they think they're going to pull in a year, or they think at that point the production might be a little bit lower, so they can just surface treatment from that point on. But that's what they went with, and that's what we made our design based on. And you can see that most of the wells got over the amount of days expected or pretty close to it. The lowest we saw was 352 at 365 days, and that's still 96% of what they expected. So I think we would consider that a success still. And if you see our longest, we have almost 900 days, 898 days, over double what they expected. So you can really see that based on our designs, we can sometimes even go really over what they expected, and our chemicals can really last as long as they need it to be. And this is just case studies on other artificial lift systems. So this is to show you some we've installed on many rod pumps and gas lifts. This is something. And then if you look at the length, that can show you the different lengths we like to design for. So we have our 24 footers, and then we have our 72 footers, 96 footers. And this is to show you that we can really install on any artificial lift system. And we residual test with most of the wells where we can see where we get that information that was Shivani was pointing out earlier. And the CD numbers to the right are just the different combinations that we can do because we can treat for many different types of chemical issues. So this is just showing you that we can become really custom when it comes to the well, since every well is different and every producer wants a different type of chemical treatment and longevity, and they have different types of artificial lifts. So I know right now with oil being around $25, $26, some operators are choosing to shut in some of their wells, and that's one of the smarter things to do. But that may come with some other problems. You may have to still chemically treat that well. You're still gonna have to have a truck come out and treat that well, or have an injection well next to it, or do batch treatment. But because when that well, with it being stagnant, it's gonna start to oxidize. And let's say you left the pump downhole, or you're still gonna have the casing in that stagnant fluid with the water oxidizing, and you start to encounter more corrosion problems, or still going to have H2S and encounter corrosion problems. And you can see any of those issues. What we would like to say is we have our droppable chem sticks. So I think this would be a simpler solution for some of those shut-in wells, because you can, based on the fluid level or anything like that, we can go maybe every 2-3 weeks, depending on some of the factors that we would analyze. It's just to drop that chemical stick down the hole. So, and then pretty much you can leave and you'll have that chemical treatment. You don't have to rely on trucks still continuously treating that well, even though it's shut in. So, and with the droppable sticks, we have applications for scale, asphaltenes, and your paraffins, your H2S, and we also have defoamers and acid surfactants. But I believe in your shut-in wells that a corrosion stick would really be beneficial if you're trying to keep that well chemically treated without having to pay too much attention to it, or take your attention away from some of your other projects that may be going on. And the chemical drop sticks can also be useful in your storage tanks, because I know in your storage tanks you may start to see some paraffin in the tank itself or in the flow line. As you can see right here to the right, this is a video of some paraffin that is coming out of the flow line after it was hot oil treated. So that would be a good benefit as well, to drop some of that paraffin drop sticks into the tank. You can prevent the clogging of some of your flow lines, and just keep some issues out the way that you're not really trying to think of at this moment with the economy with the way it is. So in conclusion, with the increased amount of sand that's being produced in the first stage of the ALS, with all that proppant or frac sand or anything like that, you may start to see some other secondary issues that you may not have thought of when you're using a desander or anything of that nature. So some of the solutions that we can offer is, lengthen the desander, increase the length of the sleeve from 2 to 6 feet. You can also change the material of the desander to have a more erosion resistant sleeve to help make sure that threading is not cut and you're not creating fishing jobs or anything of that sort. And also change the material of your dip tube to make sure it's not being eroded along with corrosion, and to make sure that can last longer. Also, with the bypass valve, you can make sure that when you get hit with a frac and your mud joints fill too fast, or your intake just gets plugged, you have the bypass valve as your secondary option to basically be your insurance tool, and to always be your secondary intake. Gas can really lead to some secondary issues that may not always be at the forefront of your mind when you hear gas, but gas can really start to create problems when it comes to your rods, to your pumps, and to your casing. May start to create more issues. So I think it'd be very beneficial to always have a proper gas separation system at the end of your pump to help mitigate those issues that you may start to see with gas. And with the ever-changing pH, a balanced chemical treatment is crucial. As Shivani mentioned earlier, The corrosion can really cause issues when it comes to your holes in tubing and weakening of threads. Your iron sulfides can start to plug as well, and the scale can start to plug and just create more issues. So it's always a good idea to have a balanced chemical treatment, whether that be surface treatment or an Odessa separator tool that you can treat from the bottom up and, design for the length of longevity that you're expecting to see from your chemical treatment. And with everything going on today, I know people are starting to shut in. Those are also having changing pH from that stagnant fluid with the oxidizing from the water starting to separate. So I believe that those droppable sticks may be a bit of use to some of those wells to help mitigate those corrosion issues or some of those other issues. And paraffin sticks can also be used in the oil tanks to help with the plugging of the flow line or any other issues that may arise from paraffin in the tanks. Thank you guys for coming to our webinar. If you have any questions, you can always reach out to me. You can see my email and number on the left, or to Shivani with her email and number on the right. And we will be here for the next couple of minutes if anybody has any questions.
And to champion what Donovan said, also, if you guys have any suggestions that we need to do or cover, if y'all find interesting on the webinars, we plan on continuing this. That way we can be in touch with you guys and just try and see what else we can cover. So please feel to go ahead and email us or contact us if there's anything else that's interesting on y'all's end, or something that is also a problem. Since we're a manufacturing company and engineers, R&Ds, we can always go ahead and here to solve the problem for sure. At least that's the mentality.
Hey, Shivani, I have a question right here.
Okay.
They are asking, when it comes to the packer type separator, if you would recommend a mechanical, or what type of packer we would recommend. In that case, that's totally up to the operator. We would say we've seen successes with both rotational or cup style packers. So we have installed with both. We have done case studies with both, and we've seen success with both. So at that point, we like to leave it up to the operator. If they want our recommendations, we'd be happy to give it to them.
Right. Also, I see that there is one saying, what is the optimal size of the helix whenever we have the start to the end of an ESP? So that's a great question. And we do deal with that a lot of times, is because whenever we're designing for an ESP, the start of the life is anywhere from a few thousands of barrels of fluid per day to going to a few hundreds of barrels of fluid per day. So in that case, what we will do is from the highest, let's say in the case of the one that we saw was 3,000 barrels of fluid per day to 800. That's something that we need to decide on the simulations that we do. What is an optimal in-between size that can handle, first of all, create that centrifugal force to go ahead and spin and separate whenever the fluid is at the highest, as well as whenever it goes down at the lowest at 800. Where is a good point to go ahead and size in between? So you don't want to create too much centrifugal force whenever the fluid goes down, as well as you do not want to create too less of centrifugal force, especially for the first stage of the well's ALS, and separate that sand particles. So that's something that we definitely go ahead and keep that in mind whenever we're designing the helix size.
Okay, I have another one. They say, have you seen any issues with foam, and how have you dealt with it? So yes, we have seen some issues with foam, especially in the Delaware Basin. We've seen, so I know foam can really be a hindrance to your gas separation, and it kind of makes it a little bit more difficult. So our solution to that, to the foaming issue, will be our chemical stick that we can put at the bottom of the hole in our chemical screen, as Shivani talked about earlier. And as I mentioned in our droppable sticks, we do have a formula for foam. So in that case, we would have our gas separator, but then below that, we would like to have our defoaming sticks help with that issue.
All right. Also, one of the questions that just got to my mind, always gets asked, is on the chemical side, is how do we know, like we mentioned before, is the chemical still there? Now, we do understand that once it's downhole and it is your solid chemical, it sticks, unlike what conventionally we're used to seeing the coupons testing on the batteries or on the surface. How do we know on down below, downhole, that the chemical is still active, it's still working? So that's exactly what I'd like to reiterate is the polytank test that OSI is efficient of doing. And what we do is with X amount of chemicals, we are going to have a certain amount of polymers. So every time the chemical is leached out, your polymer is leached out too. And that's where you have that polytank test that exactly shows you what is the ppms of the polytank and what is the minimum polytank test that you can get to go ahead and see what is the next stage. Also gives you what is the longevity that if we've designed and done expectedly on this design, or something that we need to go ahead and take a step forward to see what's the next step on it. But yeah, I think that's all the questions that we're seeing at this time. But yeah, if you guys still have any questions or would like to understand something, or if your companies would like to have a one-on-one interactions with y'all's teams or webinars, we'll be more than happy to do that. Again, thank you for y'all's time, and hope y'all have a great weekend, and hopefully we'll see y'all next week again for our next webinar. Thank you.
Thank you, guys.